Hello, my name is Thomas Carnahan, and this is my second paper for Assignment 3 of Complex 529 21B, Engineering Self-Adaptive Systems. The title of this paper is Mobile Edge Intelligence and Computing for the Internet of Vehicles. The authors of this paper are Zhang and Khaled B. Letaief. This paper was published in the Proceedings of the IEEE Volume 108, Issue 2 in 2019. The automobile industry is large and continuously growing, and with threats such as climate change, stricter emission regulations are being put in. There is also a large increase in the number of vehicles on the road, causing an increase in congestion within cities. As of this paper's publishing, there are 3,700 fatalities per day worldwide caused by automobile incidents. To manage these issues, this paper proposes implementing an Internet of Vehicles infrastructure. This consists of vehicular ad hoc networks, or VANETs. This consists of vehicle-to-vehicle communication, vehicle-to-infrastructure communication, dedicated short-range communications, and vehicle-to-everything communications. These may be used in services such as urban traffic management, road infrastructure, logistics and transportation, or vehicle insurance. Challenges that may be encountered implementing an Internet of Vehicles include processing power, of which limited may be available within a vehicle, data storage, latency between vehicle and cloud communications or vehicle and infrastructure communications, regulatory approval, and ensuring that data is safe and secure, either being stored or transmitted. Current related works include advanced driver assist systems, 90 million of which were present in 2014, growing in 2 years to 2016 to 140 million. This consists of 5 levels of automation, Level 1 consisting of small features such as cruise control, and Level 5 being full self-driving vehicles. This has seen major work from companies such as Google, Uber, Mobileye, Tesla, and Audi. One major component of the Internet of Vehicles is data, an increasingly large volume of data, which will need to be processed and sent. Some applications may require this data to be low latency. This data will also use power being processed or transmitted, which may become an issue on mobile vehicles. Edge computing may be used within vehicles to process this data, or cloud computing may use machine learning, though this will require this data to be transmitted from the vehicle to the cloud. Edge computing will play a significant role in the Internet of Vehicles. This includes wireless edge caching, where information is determined ahead of time that can be presented to a vehicle in the area. Servers at access points such as traffic lights may also be available to provide information to vehicles. Servers may be even within the vehicles themselves and may give information to other vehicles. Within the Edge Information System, this is known as Vehicle as a Server or Vehicle as a Client. Local context data is also a major part, as only information that is relevant to the area that the vehicle is in will need to be provided. Edge information systems may be deployed at roadside base stations, such as in traffic lights or along the roadside. These base stations will contain storage and computing units. They may also provide information to user devices such as phones or laptops that are being used within vehicles. These may use wireless, local area networks, or cellular communications, depending on how critical the system is being used. The Edge Information System consists of either Vehicle as a Client or Vehicle as a Server. Edge caching is the preloading of data before being sent either to a vehicle or to a base station. This consists of temporal locality-aware caching, spatial locality-aware caching, and mobility-aware caching. When a vehicle is acting as a client, temporal locality-aware caching must take into consideration the freshness of the data, as new maps may be updated quite often. Requests may also vary with time, and the time of day. When the vehicle is acting as a server, there may also be limited resources within the vehicle, and the file sizes may need to be taken into consideration, with larger files being flushed out quicker. For spatial locality-aware caching, when the vehicle is acting as a client, the freshness of the data must be taken into consideration, as well as the location of the vehicle, which may change quite frequently. When the vehicle is acting as a server, information to be cached may also be based on the location history of the vehicle and where it was in previous times. Multi-hop connections may also be used to transmit data to a destination through multiple other vehicles or base stations. When a vehicle is acting as a client, mobility-aware caching must take into consideration the file sizes of the data to be received, as intermittent connections may be encountered as the vehicle is moving. When the vehicle is acting as a server, it must also take into account the vehicles that are traveling nearby and what information they may want to receive. And if they're traveling to the same destination, could we share information with that vehicle? One application of edge caching is perception and localization. This may include autonomous overtaking, collision avoidance, or a bird's eye view that may be available to the driver. Other applications include InfoRank, where a vehicle may be pre-selected to collect certain information based on either where it's been or where it's going. Another is over-the-top, in which the popularity of information is considered so that the information may be cached ahead of time. Secure information sharing may contain data such as vehicle location for tracking purposes, and traffic control may determine where a vehicle is going and have that information cached and ready for traffic control. Another major component of the Internet of Vehicles is edge computing. This is when data is processed within a vehicle or a base station and not necessarily in the cloud. This will play an important role in vehicle as a client and vehicle as a server communications. This enables ultra-low latency, lower energy consumption, and enhanced privacy, as there is no communication with a cloud server. When a vehicle is acting as a client, edge computing may consist of base stations containing graphics and tensor processing units. These may be placed along roads. These may communicate with vehicles using 5G networks, with applications running on virtual machines on the nodes. Two attempts in the past have been OpenVDAP and CavBench. Resource management is a big part of this, as it must be decided if an application is going to be run on the vehicle or within the node. It also must be decided who is going to run this application. Efficiency must also be taken into account, as data must be sent over a wireless network that consumes energy. When a vehicle is acting as a server, edge computing may consist of a powerful processing unit within the vehicle, such as an NVIDIA drive. This may be used for surveillance, traffic management, or self-driving purposes. Vehicles may also share resources between each other, and incentivization schemes may be used. Some applications of edge computing include driver identification, which may be used to set profiles within a vehicle, such as seating position or steering wheel position. It may also be used for security to ensure that the driver is not a thief. They may also be used for traffic estimation to ensure efficiency within traffic flows and ensure as little time as possible to get from one destination to another. Public safety may also utilize this, using cameras on board vehicles for surveillance, or to plot a path for emergency vehicles and have vehicles move automatically. Edge artificial intelligence utilizing machine learning algorithms may also be used in the Internet of Vehicles. This may be assisted by edge computing, either within a vehicle or within nodes placed along a roadside. This may have applications such as perception, mapping, and simultaneous localization and mapping. Two edge AI frameworks may be used. This includes federated learning, in which data is collected by a vehicle, and a machine learning model is trained on the vehicle itself. A remote processing server then collects these models from all vehicles. This ensures privacy as the model is trained on the vehicle itself. The other framework is the Joint Device Edge Inference. In this, computations are segmented between a remote and the local processing server. This shares resources between each server. This may cause high latency, high energy usage, and would require significant load balancing. When the vehicle is acting as a client, Edge AI may be used for edge-assisted perception. In this, nodes may perform object detection and tracking, offloading this computations to a cloud-based server. This may also be used for edge-assisted map updating, where edge devices monitor changes in traffic and determine the data that will be sent to the vehicle. Edge-assisted SLAM. This may be processed in the cloud, while edge devices collect data and send it to each vehicle. With vehicles acting as a server, Edge AI may be used for cooperative perception. This includes see-through, bird's eye, or satellite view. This will be done using vehicle-to-vehicle communication. Crowdsourced mapping may also be possible, as necessary hardware such as cameras are on the vehicle. This would require a large amount of data to be collected and processed on vehicle. There is also multi-vehicle SLAM, in which SLAM is processed on each vehicle and data is collected and merged between vehicles. Three major components will take a large role in the Internet of Vehicles. This is edge caching, edge computing, and edge AI. Challenges include the integration of these systems into existing infrastructure, the regulation of these systems, and the standardization to ensure they can be continually improved and upgraded. Critiques of this implementation include the cost. Processing units within vehicles, nodes, and remote servers will cost a lot of money to implement. There's also privacy, as large amounts of data will be sent to and from the cloud, with surveillance being a large part of this. The end of life of components is also a major factor, as these systems will be continually upgraded as new technologies advance. There's also the reliability of this system, and ensuring that all vehicles know what to do if a component of the system fails. Thank you.